Now it's 1 year ago that we started with the 3D-Print Harrier project, so it's a good time to take a look back, what happened, what did we learn and what will be the next step for future. At the beginning we spent a lot of time to understand and improve the Harrier ducting to get much as possible thrust out of it. To make the airflow visible, we put red strands on the nozzles and tried a lot of different turning vanes to get a much clean airflow inside for the maximum thrust. Here we can see the turning vanes also inside the ducting, but at the end this gave no advantage, so we let the turning vanes just in the nozzles. Okay, so this time we got nozzles here with 4 turning vanes. The next step was to evaluate the optimum number of turning vanes into the nozzle. We started from 2/3 to 4. We figured out the optimum at 3 turning vanes, and this is what we use till now. Nevertheless, there was a big loss of thrust into the Harrier ducting, so we made different thrust testing, at first just with the ducting and afterwards with nozzles installed. Different brands were tested, and at the end we got the best results with the all metal JP 90mm EDF fan. And this is completely 3D printed. We got already a complete CAD model of the Harrier, so we decided to print the whole thing in lightweight PLA. The composite lightweight construction to the 3D. The challenge on this part was to keep the weight as light as possible, and I orientated myself on the composite lightweight technique I was using years before on my SUX with these glass fiber honeycomb composites. Also want to see how it will fly and will act. Beside the weight reduction, we want to improve at the same time the lift of the wing that is quite small on the Harrier, and so we tested some different vortex generators. Parallel to all the improvements on the Harrier, we had to fight with a lot of problems on the print technique itself, especially on bigger parts. We got a lot of failures in the surface, so a lot of adjustments became necessary on the Cura slicer. But at the end we reached our goal to print most of the Harrier structure with 1 outer layer and 9% infill, and this was quite amazing to see how lightweight it could be. This is one of our very first attempts of the vortex generators to test different styles. We made them as separate part in front of the wing. You can see this here. This is SUX main fuselage. The Harrier benefits a lot of my experience with the SUX project. That means not just the lightweight composite technique, also the installation of the servos, of the gear, and a lot of other details. Lightweight print, that's the idea. Here we can take a look into the structure of a wing, which is currently printed. Inside is the gyroid infill. All around is 1 layer wall. All is printed in lightweight PLA. Lightweight composite part. Right after all optimizing of the lightweight PLA print settings, it was not possible to reach the same weight to strength ratio like we got on the composites, but nevertheless it was good enough to go on with the Harrier lightweight print project. Outer and 1 inner layer, 2 bottom layers. And here's the same wing This is printed just with a shell. This I think is about. Here we can see the difference between lightweight and normal PLA. While in normal PLA it's common to use just one outer layer. On lightweight PLA this would be too soft, so we have to use some gyroide infill in between and make the all thickness of the wall much bigger than it is used on normal PLA. This is rotatable. Now it was time to check the lift on different vortex generators. For this I built a test stand where the wing could be adjusted on different angles of attack. I prepared already this. This is a brush. To sweep the wing, a 60mm brushes was made, which has 2 ball bearings on the end. Then a wing extension was cutted on a styrofoam cutter. With the rotatable attachment for the wing and a anemometer to see the wind speed, and here are the 4 EDFs. In front of the wing was a wind speed gauge, and the whole wing with the sweep construction was put on a scale to see how much lift it will produce, and the wind itself was made by 4 strong 90mm EDFs. The result showed off that we got the most lift with the semicircle and straight mounted vortex generators.
Okay, welcome everybody to another video.
On February 2022 it was time for the maiden of our lightweight printed Harrier, and for this big milestone our VTOL buddy Joel came over from Netherlands and he brought with him his big Harrier, so we could also do a lot of knowledge exchange and see how we bring our projects to life.
Nice to have you here. Better.
Joel is building the AV8 in a much bigger scale than our ones with a 120mm EDF, also printed in lightweight PLA.
I will finish this vertical start and then we can combine these models together to make a first.
It was very interesting to see how Joel is working on all these special difficulties on the Harrier, especially stabilizing while hover. And so we could learn a lot from each other, and this is always big fun when we see us in our workshops. We were very happy that we reached a thrust to weight ratio from over 1, so the Harrier won't go up vertical into the air. After this last stress test for the battery, the ESC and even the EDF, we were sure that it's time for maiden.
Yeah, it's flying. It's flying.
Happily, some aerodynamical difficulties could be fixed by the immense power of the Harrier, so that we were very lucky that nothing goes wrong on its maiden flight.
Langsam mit dem Anstellwinkel. Ja. Nö. Naja, ein paar Runden zeigt das noch. Ich merke noch, der wackelt da ganz schön.
What? Looping?
No. Looping?
But it was obvious that a lot of changes are necessary, especially the fuselage was too small, that the flight characteristics are too unstable, so we made the fuselage 10% bigger and we also enlarged the vertical and horizontal step to give it much better flight performance. We also decided to go the next steps and give the Harrier full VTOL ability. Of the Harrier, like today, this rotating nozzles. So we started to improve every detail. Here, for instance, the ESCs. We are using for the first time the latest technique, the so-called Pro Shots. This is a 200 amp ESC, which has just half of the size and weight from the normal technique. But this has to be extra configured, means we have to put on our own cooling and also the cabling. These high-end ESCs are super efficient and stay very cool even on high current. So everything is ready for the first thrust testing. Here we can see the temperature, the moment 17 degrees. This is our thrust, and here we got the watt meter for the amps. On this thrust test we installed the first time sweepable nozzles. While on the first test on 80% power everything works well, on the second test on full throttle 3 of the nozzles flew away. So we couldn't go on with these full rotating servos with end switches. This wouldn't work safe. No, this time all 4 nozzles were blown away. We have to work on this. Here we got our Pro Shot ESC 200 amps. This works really nice. The max temperature was about 60 degrees and it even cools fastly down. At the moment there is no extra cooling installed. The JP fan 90 mm, and we got our motors. These are rebuilt servos. We changed the electronics to a small ESC, and this is driven by this electronic. This is coupled with 2 end switches. The end switch we can see here, one side, and also we got one on the other side. And these noses up there, they run on the end switch, so the rotating stops. Yeah? When I make the switch here, you can see the motor start rotating endless. And also the other direction. Yeah, this is a 3-point switch, and in the middle position there is no rotation, and the rotation stops when I touch the end switch. At this point we stand for a really big challenge because we need servos that could rotate controlled nearly 360 degrees, but at this moment we didn't find them on the market. So what could we do? That can be programmed to rotate about 360 degrees. A servo, here I tried to modify 180 degree servos with different resistors to make them move nearly 360 degrees, but this doesn't work well, so we stopped it. And we found them. We found special high-tech servos with a magnetic encoder. They can be programmed. Luckily, one guy of our VTOL group gave us the clue that high-tech made these special servos with a magnetic encoder, and they can move around 340 degrees, and this was exactly what we need. Another challenge to solve was the yaw stabilization. Here is our first design with these 2 horizontal installed EDFs. We don't think that it is the best solution and we didn't test it. And parallel to these challenges, we were forced all the time to make the whole construction more and more lightweight to make VTOL reality. starting assembling the Harrier wing, and at first I put these small pins, they are also printed from lightweight PLA, into the holes there on the wing. They are for positioning. And here we got the wing. One piece, just some minutes of gluing. Fits perfect. Now it's time for reinforcing the wing. Here we can see the gap for the upper spar cap. I will use carbon rovings for this job. While at the moment we do just bungee starts with the Harrier prototypes, in the background we are already developing a retractable landing gear. But this seems to be very difficult because it should be super lightweight and also super stable, and here you can see our first attempt. Time for the Harrier landing gear. It's a bit too long, doesn't fit. Hey, next problem. Works. In contrast to other aircrafts, the main landing gear of the Harrier is not close to the CG. The CG is nearly in the middle between the front and the main landing gear, so both has to be super strength. Let's go to the next one. While our first attempt of the landing gear was made on metal, we have the goal to make the most of the gear, made it printable, so we did also the first test with aramid reinforced PLA. And this is printed from AF80. This is a aramid reinforced. For stress testing the landing gear, an extra machine was built which simulates rough surfaces like a grass airport. Begins, there's not enough material inside, so we have to reinforce this. To the one before, this one is just printed in AF80. This also broke right there. Meanwhile, the test flies goes on. We got one big problem. This was on the start ramp, and while leaving the ramp, the Harrier has a bank angle of nearly 90 degrees sometimes, and this was really dangerous. So we have to improve the start technique. And we figured out that it makes sense to give about half throttle right before the rubber gets loosed, and when the EDF is nearly rotating full, when the Harrier is leaving the ramp, then we don't have this big side angle after leaving the ramp. With this onboard cam on the front, we could make the airstream on the upper side of the wing visible, and so we could improve again the wing design to make the Harrier fly most comfortable as possible. An ESC failure caused this little outlanding on the cornfield, and here we got a first impression how tough the 3D printed construction is, because the damage was really little and it could easily be fixed with super glue.